As we start this last section in Chapter 1 on infinite limits, and we're going to have a definition of an infinite limit, which is going to be somewhat similar, a little bit anyway, to the epsilon delta definition that we had of a limit back in Section 2. I've mentioned in at least two of the previous videos that one of my professors had handwritten an epsilon delta proof that he was doing in class when he ran out of time. He handwrote each one of the members of the class the solution and handed them out to him, to each one of us on the next class meeting. Well, this is 40 years old, but it's still in pretty good shape. I laminated it, and there was a limit as x goes to 2 or 3x minus 6 all over x squared minus x minus 2 is equal to 1. Now, if you try to use direct substitution, you're going to get 0 over 0. So you would have to approach this a different way, probably algebraic, probably factor the numerator and denominator, see if something cancels. But by definition, you would have to do an epsilon delta proof, and as you can see, Dr. Regenberg set his up, and the QED at the end is traditionally written down at the end of a proof. It's representing Latin words, quod erit demonstrandum, which means what was to be shown. So when you see that, or sometimes EOP, end of proof at the bottom, you know that that's the end of the actual proof, or that's been shown and demonstrated. Anyway, I thought you'd get a kick out of it. Maybe not. So I'll move this over here, and let's go to the idea of infinite limits. All right, now infinite limits means that instead of the limit approaching a set number, that our limit is unbounded. Now we know that when a limit is unbounded, that the limit does not exist, but we can at least describe to a certain point what's going on with our limit if we use the infinite notation. So let's consider the function f of x equals 1 over x minus 1, and let's look at the limit from the right and the limit from the left. And you can see here from the left side, my numbers are getting smaller and smaller and smaller. From the right side, my numbers are getting bigger and bigger and bigger. Now, graphically, we know that this function at 1 has a vertical asymptote, and then our graph looks something like this. This is really, really rough. And you can see there, as x approaches 1 from the right side, this is a 1 here, you can't really see that the numbers get bigger, that it goes upward, and as x approaches 1 from the left side, that the numbers get smaller, absolute value-wise get bigger, but the numbers get smaller and are unbounded below. So a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Now, the definition of an infinite limit, I'm just going to kind of state we don't have to actually do any proofs as far as being able to use this kind of a definition to prove that of an infinite limit example, nor do we have to do the epsilon delta proofs. But it's something that should be stated all the same. And so the definition of an infinite limit, let f be a function that is defined at every real number in some open interval containing c except possibly at c itself. You know, the limit doesn't exist at c. The statement that the limit as x approaches c of f of x goes to infinity means that for all m greater than 0, there exists a delta greater than 0 such that f of x is greater than m whenever 0 is less than the absolute value of x minus c is less than delta, which is saying that as x gets closer and closer and closer to c, our f of x value gets bigger and bigger and bigger and bigger. And when we have that happen, we say that the limit is infinity. Similarly, the statement the limit as x approaches c of f of x is negative infinity, means that for all n, capital N less than 0, there exists a delta greater than 0 such that f of x is less than n, as a small number is unbounded below, whenever x is very close to c, when the absolute value of x minus c is greater than 0 but less than delta. So, with all that stated, let's look at some actual examples. What happens as x approaches 2 from the right side? Well, as x approaches 2 from the right side, let's just think of this kind of a little bit of arithmetic in our head. A little bit bigger than 2 minus 2 is a little bit bigger than 0. A little bit bigger than 0 dividing into 1 gets big. 0.1, 0.01, 0.0001. If my denominator is getting smaller and smaller and closer and closer and closer to 0, but it's positive, then I have 1 divided by really small positive numbers, which is a very big positive number. So we say that the limit is infinity. Now, I know that when we write this down, it means the limit does not exist, because that's one of the types of problems when we were looking at limits back in section, I think it was section 2, that said that the limit didn't exist. The limit from the left doesn't equal the limit from the right, things like that, or if it oscillates. But we're going to write infinity now down because it describes why it does not exist, that it is unbounded above. Now here, as x approaches 2 from the left side, the limit as x approaches 2 from the left side of 1 over x minus 2. So this would be a little bit smaller than 2, 1.9, 1.99, 1.999999. Well, if I plug those numbers in and I subtract 2 from it, I also get a number very close to 0, but negative. Very, very small absolute value-wise, very, very close to 0, but a negative number. And 1 divided by these types of numbers goes to negative infinity. So you can see that the reason why this limit does not exist is that it approaches negative infinity. Now here, the two-sided limit, well, the one side goes to positive infinity, the other side goes to negative infinity. So we're not going to write down plus or minus infinity. We're just going to write down that it does not exist. Okay? And very, very similarly, I don't know why I have these 3 examples, but I have them all the same. The main difference is that the numerators are now negative 1. Well, you have a negative 1 divided by a really, really small positive number. This is going to go to negative infinity. Negative 1 divided by a really, really small, close to 0, but negative number. Negative divided by negative is positive. This is going to go to positive infinity, and this is still not going to exist. Now, if they give you a graph, as I have in G here, and I have a function y equals g of x, and at 2, you can see I have a vertical asymptote. I look at the limit as x approaches 2 from the left of my function. From the left, it's going upward, so it's going to positive infinity. From the right side, as it approaches 2 from the right, 2.1, 2.01, 2.0001, what happens is that it's also going upward. It's getting bigger and bigger, so it goes to infinity. Now, for the two-sided limit, we can certainly say that it goes to infinity. Now, notice here we have an infinite limit at a vertical asymptote. So I got a feeling that there's going to be some kind of a tie-in between this type of a limit and the vertical asymptotes of particularly rational functions for the most part. Let's see if we can tie those together. We can. Let's define a vertical asymptote. Now, this is a calculus definition of a vertical asymptote because it has to do with the limit. The line x equals a is a vertical asymptote of the graph of the function y equals f of x if either the limit as x approaches a of f of x is either positive infinity or negative infinity, or the limit as x approaches a from the left side of the function is either positive infinity or negative infinity. So since we have rational functions with vertical asymptotes, that's where we're going to start. So here's a theorem with some vertical asymptotes here. Let f and g be continuous on the open interval containing c. Let f of c not equal 0 and g of c is equal to 0. And there exists an open interval containing c such that g of x does not equal 0 for all x not equal to c in the interval. That's a lot to say. Then the graph of the function given by, notice the rational function here, h of x equals f of x over g of x, has a vertical asymptote at x equals c. So what they're saying here is at x equals c, it's going to make the denominator 0, but not the numerator 0. But what happens here is we look at the limit, we're going to either get positive infinity or negative infinity. Look right here. It says find all vertical asymptotes of the graph of each function. Now we know how to find vertical asymptotes from back in Algebra 2 and even in pre-calculus. We look for those values that make the denominator equal to 0, but not the numerator. And I would get here 2 possibilities, x equals positive 1, x equals negative 1. Those would be my vertical asymptotes. Now to show that they're my vertical asymptotes, let me take the limit as x approaches, let's start with positive 1, and let's just go from the right side here, of 3 all over x squared minus 1. Well, a little bit bigger than 1 squared is a little bit bigger than 1. Minus 1 is small, close to 0, and positive. 3 divided by really, really, really small is really, really, really big. And based on the definition of vertical asymptote, I have a vertical asymptote at x equal 1. Now if I take the limit as x goes to negative 1, let's go from the right side as well. Doesn't matter, either one will work. And as x goes to negative 1 from the right side, that would be a little bit bigger than negative 1. Negative 0.9, negative 0.99, negative 0.999999. When I square those, I'm going to get a number a little bit smaller than 1. Minus 1 is close to 0, but negative. Very, very close to 0, but negative. Well, 3 divided by negative small is negative big. If that makes sense to you, this is going to go to negative infinity. So I also have a vertical asymptote at x equals negative 1 by definition. Now, in this problem here, there's only one vertical asymptote that's going to occur because there's only one value here at 2x plus 5. So you could set the 2x plus 5 equal to 0. I get 2x equals negative 5. I get x equals negative 5 halves. I have a vertical asymptote. I know that I have a vertical asymptote at x equals negative 5 halves because it makes my denominator 0 but not my numerator. To prove it, though, I would have to take the limit as x goes to negative 5 halves from either the right or from the left of my function g of x. Well, if I go from the right side, this is negative 2.5. It would be like negative 2.49, negative 2.499, negative 2.49999. And if I plug that in, I get a number that's very, very close to negative 5, but just a little bit bigger than negative 5. Plus 5 is going to be a number that's going to be very, very close to 0, but positive. Up top, I'm going to have negative, looks like 4.5. So negative 4.5 divided by a very, very small positive number is a very, very big, absolute value-wise, big negative number. This is going to go to negative infinity. So I have a vertical asymptote at x equal negative 5 halves. Now, they don't always want you to prove it, but this is how you would go about to prove it. I don't think I'd really care to have to do a whole bunch of these because we know with secant of x, there are many vertical asymptotes because secant of x is 1 over the cosine of x. When is the cosine of x equal to 0? Well, the cosine of x is equal to 0 at pi over 2 plus pi k, where k is an element of the integer. Excuse me, I almost said real numbers there. This is one of the reasons why we studied how to solve trig equations for just this kind of situation here. And so now all my vertical asymptotes, infinitely many vertical asymptotes, would be x equals pi over 2 plus pi k, k be an element of the integers. Now, I would not want to have to verify each one of these because there's infinitely many. I'm sure there's a pattern that I could develop, but in this case, these are my vertical asymptotes. And notice again how my vertical asymptotes are written. Not just the number, not just 1 or negative 1, not just negative 5 halves, but the vertical asymptotes are a line. So it are lines, I should say. So it should be in the form of the equation of a vertical line, x equals, x equals, x equals, even here, x equals. Okay, now, if the value of the numerator and the denominator at x equals c are both equal to 0, then as I mentioned before, we have what we call an indeterminate form, 0 over 0. And we have a hole in the graph. I kind of spoiled that in the previous section. We have a hole in the graph. That does not mean we have a vertical asymptote. It just means that we have a hole in the graph. We have a point of discontinuity. So if I ask for you to determine all vertical asymptotes of this graph. Now notice it just says determine. It does not say to verify. So I'm going to first factor, and I hope that you can see this okay. It looks like you can. X minus 2 times x minus 1 all over x plus 1 times x minus 1. You can see that at x equals 1, it makes the denominator 0 here, but it also makes the numerator 0. So I don't have a vertical asymptote. I have a hole in my graph at x equals 1. But I do have a vertical asymptote when x plus 1 is equal to 0 or at x equal negative 1. There's my vertical asymptote. Okay? Now, we're going to take from this and we're going to get some properties here of these infinite limits, and then we're going to try to evaluate a few more of these. Here are some of the properties of infinite limits, and notice how similar they are to some of the properties that we had with other types of limits. There's not really a scalar property because when you multiply by a constant, it's, you know, and your expression is going to infinity or negative infinity, it's just still going to go to infinity or negative infinity, kind of based on if the constant is positive or negative. So in this case, theorem on the property of infinite limits, we let c and l be real numbers, and we let f and g be functions, such that the limit as x approaches c of f of x is infinite, infinity, and the limit as x approaches c of g of x is finite, equals L. So what's the sum or the difference of a limit where one is going to go to infinity and one's going to go to negative infinity? Well, the limit as x approaches c of f of x plus or minus g of x is infinite, because this is going to infinity, positive infinity, and it doesn't matter whether you add or subtract a positive number or a negative number, it's not going to affect it, even if the number is very large absolute value wise. This is going to go to positive infinity. The limit here as for the product as x goes to c of f of x times g of x, well, if L is positive, you're multiplying, kind of multiplying like the idea of infinity, something that's bounded by a positive. Positive times positive is positive. But here times a negative, if L is less than 0 for g of x, then it goes to negative infinity. And the quotient here, the limit as x approaches c of g of x over f of x, well, if the denominator is going to positive infinity, it doesn't matter how big this number is, how small this number is, when you're dividing it by a very, 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 very large number, this is going to go to 0 itself. So it says here, all these properties that I mentioned are all two-sided limits, but they work for one-sided limits as well as for the f of x going to negative infinity. It's very similar if it goes to negative infinity as compared to positive infinity. So let's look at a couple, 3 examples here. All right, we're to evaluate the limit as x goes to 0 of 3 plus 1 over x squared. Well, as x goes to 0, since it's squared, it doesn't matter if it goes to a positive or negative. This is going to be a really small positive number. So 1 divided by a really small positive number is a really big positive number. Add 3 to it, even bigger. This is going to go to positive infinity. Now, I didn't show any work, but I kind of explained it in words as I was going through it. So if you have a problem like this and you write down your answer and you don't have any kind of an explanation written to the side and your answer is wrong, it's going to be tough to figure out why it's wrong, and were you on the right track and made a silly mistake. So it might be best on some of these problems where it asks you to evaluate it, if maybe next to it in a sentence or two you kind of give a description of what you did to compute that and to figure that out. Now here, the limit as x approaches 1 from the left side. So this is going to be a positive number, but it's very close to 1.9.99.99999. Well, if this is approaching 1, then this is approaching pi. And the cotangent of pi, okay, it gets a little weird here. The cotangent of pi, well, first off, hang on, let's just, before I jump the gun too much, this is going to go to 1 squared plus 2. This is going to go to 3 up here, but this is going to approach the cotangent of pi. Now the cotangent of pi is the cosine of pi over the sine of pi. The cosine of pi is -1. The sine of pi is 0. So you say, well, wait a minute, what does this mean? Well, this means that my denominator is getting really, really, really big. But is it getting big positive or is it getting big negative? Well, if I'm approaching pi from the left side and I'm plugging in numbers from the left side, this is getting really, really big. The graph, let's see if I got this right here, of cotangent, let's see here, put pi right here. Actually, this is getting really, really small. It would be nice if I knew what I was talking about here. It would go something like this. So this is going to be going to negative infinity from the left side here. Is going to negative infinity, and 3 divided by numbers that are unbounded, this is going to get closer and closer and closer to 0. Okay. Now, last but not least, and I'm going to rewrite this as the limit as x approaches 0 from the right side of 5 over the sine of x. I'm just better with signs here. Now, as x goes to 0, the sine of x is going to 0, but it's going to 0 from the right side, and we know for sine that it kind of does one of these kind of graphs here at 0. So from the left side, it's approaching 0, but it's negative, but on the right side, it's approaching 0, but it's positive. So this is getting really, 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 really close to 0, but it's positive, and 5 divided by really, really, really close to 0 is going to go to positive infinity. Now, I just feel uncomfortable with my explanation here. The cosine of pi over the sine of pi would be -1 over 0. So this is getting big without bound. And for cotangent, yep, I think I have this set up right. That this is going to be going to negative infinity, and 3 divided by really small number absolute value-wise, a very big number is going to go to 0 here, and this makes sense. So hopefully, if you were having some concerns about some of the different kinds of limits, whether they exist or didn't exist, we can describe certain types of limits that do not exist by the fact that they are infinite limits, and we can write that as positive infinity, or in some cases as negative infinity.